Welcome back to Algorithms and Uncertainty. Today and also next time we will be considering problems of stochastic probing. These problems are somewhat similar to the problems of optimal stopping that we saw, but they are also different in certain ways. What is similar? Well, the similarity is that again we will be seeing certain prizes, and out of these prizes we can take home at most one. But what is different now is that, first of all, we do not immediately, when we see a prize, have to decide irrevocably whether we take this home or we discard it, but we may actually keep exploring after having seen a prize and then still may take this home. And another difference is that we are now the ones choosing the order in which the prizes are presented. We'll be seeing two different variants of a very similar problem, but although the problems feel very similar, the results are actually very different. For the problem that we'll be seeing today, we will be able to define an optimal policy, and we will be able to just express this quite easily. Next time we will see a problem for which the optimal policy is pretty difficult, and we cannot even compute this optimal policy. But as I was saying, today everything is easy, or at least the final description will be easy. So let's see what our problem today looks like. We have n boxes, and there are prizes inside the boxes. So Vi, this is the prize inside box I, and I will be just something between 1 and n. And these Vi are drawn from probability distributions Di independently. And this Di, this is a probability distribution which is known in advance. And we have, as a Ci, we have the cost of opening box I. One thing I should mention is that here these Di, they are not necessarily identical. And what is it that we now want to do? We may open as many boxes as we like. And we would want to maximize what? We would want to maximize the prize that we take home, and we're allowed to take only home one of these prizes. But we'll have to pay for every box that we open. So once again, we may open as many boxes as we like. So we may open all n boxes if we like. But we're taking home at most one of the prizes, but we have to pay for each of the boxes that we open, so this is why we have a maximum here and a sum here. This problem is known as Pandora's box. And if you're familiar with Greek mythology, you will realize, okay, maybe this is not the most meaningful choice of words here. If you don't know Greek mythology, please do figure out what Pandora's box is actually all about. The similarity here is that, well, once we open a box, this box is open and we cannot close it anymore. Although, well, we might not be happy with what we find inside because we can take home at most one of the prizes that we find. So we might indeed regret opening certain boxes because they turn out to be empty. But that's okay in this case. So what could this look like? We might have the following setting. We might have two boxes. And let's say that the first prize is 4 with probability a half, and it is 0 also with probability a half. So these are the only two values that we can see for this box. And what's the opening cost of the box? Opening this box costs 1. And what do we find in the second box? In the second box, we find a price of 2 with probability 1. And the cost of opening this box is also 1. Now, what would you do now? What could you do? You could start by maybe opening box 1, and then, depending on what you find, you might want to open box 2. Or you might want to first open box 2, and then open box 1. What is the optimal choice here? Indeed, the optimal policy is that we open box 1 first, and if it is empty, we open box 2. And what's the expected reward? Well, with probability a half, we'll open only the first box where we find a price of 4 and we'll have to pay 1. And with probability a half, we find 0 inside the first box, but then we'll find a 2 inside the second box, and we'll have to now pay for opening each of the boxes. So this means that here we're getting a 0, here we're getting a 3, and so this is why the expected reward will be 3 halves. One thing we should notice is that here, if the first box turned out to be empty, then we open the second box. Only because we open the second box we break even. Otherwise we would have, well, a price of 0 and we should pay a cost of 1, so we'd have an expected reward of -1. There are also other policies. What could you do instead? You could, for example, open the second box first. Then you'll have an expected or a reward of 1. And then, depending on whether you want to do this or not, you could then open the first box. But this actually won't change your expected reward. If you do the math, this will always give you only an expected reward of 1 if you open the second box first. So this is where you see, okay, this will be the optimal policy. But what do we do in general? How do we in general get to the optimal policy? So here it is kind of easy because there aren't too many policies. How can we figure out in general what the optimal policy looks like? To do this, we'll now first consider the case of just a single box. Would we want to open this single box or not? Well, this is actually somewhat easy because this only depends on one probability distribution. So depending on what we find there in expectation, we would want to open the box or not. But then the amazing thing is that we can combine this result for only, or that we can use this result for a single box for all of the boxes, and then suddenly we get an order in which we want to open all the boxes. Let's now talk about the problem of just a single box. Would we want to open the box or not? Well, this depends on the probability distribution, which price we can find inside on the one hand, and on the other hand, how much it costs us to open the box. We certainly wouldn't want to open the box if the cost of opening it is higher than the expected reward that we find inside, or the expected price. So this is why now we say that without loss of generality, we can say that the cost of opening a box is at most the expected price that we find inside. Because otherwise we can just ignore this box entirely. So there is one thing I should have said maybe, namely that if we open no box, then the price that we're taking home is 0, but of course also the cost that we're incurring is 0. So this means that we never actually have to open boxes. And therefore we can, without loss of generality, assume that no box is more expensive to open than what we find inside in expectation. Such a box we would never want to open. This is clear if we have only a single box, but even if there are multiple boxes, things will only get worse. Good, so this is the case that we are focusing now on. Now let's try to better understand this case of just a single box. When would we want to open this, or how can we understand how much we are getting from opening this box? Which we will be later on also seeing in the context of multiple boxes. Well, let's first understand the following setting. Suppose there is one investor, and this investor approaches us and tells us, well, you know, I can open this box for you. I pay the cost of opening the box, but this means I will take some of the price that I find inside this box, and you keep the rest. And to be more precise, this investor tells us, well, you know, I take everything that we find inside this box above a certain cap. This is what I want to take home as my compensation for having paid the opening cost. You keep everything below the cap. And the question then is, well, would this be a good deal for the investor or not? Let's first try to write this down a little more formally. So we now introduce a cap which we'll call sigma I. And based on this cap, we now define a capped value, which we will write as kappa I, and this is Vi if Vi is at most sigma I, and it is sigma I if Vi is bigger than sigma I. So in other words, this is just the minimum of Vi and sigma I. So this is what we will be getting from a box eventually, now that the investor comes and tells us, well, I cap your value at sigma I. Everything exceeding sigma I, I'm taking away from you. So then this means if we find a price of at most sigma I, then we're keeping everything. And if we're finding more than sigma I, then we'll only get sigma I. So it's just the minimum of the two. The reason why we're doing this, why we are hiring this investor, why we're giving away something above this cap, is that this investor is paying for us for opening this box. So how much is the investor taking home? This is what we call the bonus. We write as BI, and this BI will be equal to Vi minus sigma I if Vi is bigger than sigma I and it is 0 otherwise. So this we could also write as the maximum of Vi minus sigma I and 0, or we may also write as Vi minus kappa I. So this looks maybe a bit complicated, but the general idea that you should keep in mind is that we cap the value at some point. Everything that's below the cap, this will be the cap value. Everything that is above the cap, if anything, this will be called the bonus. Let's see this in our earlier example. We had this box where we find a 4 inside with probability a half, and it turned out to be empty, also with probability a half. Now, what will these random variables up here look like? Well, this now depends on the cap that we're imposing. Let's say the cap is at least 4. Then we'll always have that kappa I equals Vi, so the bonus will always be 0. Everything will always be, the cap value will always be the full value. Now the more interesting case is probably that the cap is somewhere below 4. What will things look like then? Then we'll have that kappa 1 is equal to sigma 1 and B1 is equal to 4 minus sigma 1 with probability a half, and kappa 1 is equal to 0, B1 is equal to 0, also with probability a half. So this now depends just on our value of the sigma 1, how much we are as the one who's taking home the prize. The capped value we are taking home. This is how much the investor is taking home. This, of course, now depends on the respective values. So what are now the expectations of the two? How much is everybody taking home in expectation? The expectation of kappa 1 will now be a half times sigma 1, and the expectation of the bonus will be a half times 4 minus sigma 1. So this will be 2 minus sigma 1 divided by 2. So depending on the value of sigma 1, this might not be a good deal for either us or for the investor. Namely, the setting that we were considering was that opening this box costs 1, and this is what the investor is paying. So how much are they taking home? Well, they are taking home the bonus, but they also have to pay for opening the box. Opening the box costs 1, so how much will the investor eventually take home? This is the bonus minus the opening cost. So, under what circumstances will this expectation be positive? Under what circumstances will this expectation be negative? Well, this now depends on sigma 1. So, will this in expectation be more than the cost of opening the box, or will it be less? Well, this really depends on sigma 1, and what we see is if we set sigma 1 to exactly equal to 2, then this investor in expectation exactly breaks even. Because then the expectation that we're getting from B1 is exactly 1, which is the cost of opening the box. And this is what we call a fair cap, because now the investor is in expectation breaking even. They are not making money from us, but they are just taking away the risk from us. So we'll now write the fair cap. This is a choice of sigma. Or sigma I to be precise, such that the expectation of BI is equal to the cost CI. Such a thing exists for every box. Why? Always exists, and why is this? Well, the expected bonus, recall how the bonus is defined. This is the expectation of the maximum of Vi minus sigma I and 0. And the important thing is that this is a continuous function in sigma I. And for sigma I being 0, we'll have that the expectation of BI is nothing but the expectation of VI. And for that, we said, okay, the expected price that we find inside a box, we say is always at least CI. And if we now consider the case that sigma I goes to infinity, then how big is the expectation of BI? Well, this will be 0, because we're just subtracting everything here, so we're not getting anything. And this will certainly be no more than the cost of opening this box. And so this means, because this is a continuous function, that there has to be a sigma I for which we have this exact equality. And let's go back to our example. As I was already saying there, we had that the expected bonus is 2 minus sigma 1 over 2. So if we now say this should be equal to 1, which is the cost of opening this box, then what we'll see is that sigma 1 has to be exactly equal to 2. So we have now the definition of this fair cap, which is exactly the amount at which we should cap our value such that this would pay off for an investor. The investor would always cover the cost of opening the box, and they would take, they would actually cover the risk. They would keep everything that is above the cap, and we keep everything that is below the cap. And the interesting thing is now that we can actually turn this into a general policy for multiple boxes. Namely, what we'll do is we will open the boxes by decreasing fair cap, because the fair cap, so to say, is somewhat a surrogate of how much we can expect from a box. We'll now come to the problem of multiple boxes, and for this, having this understanding of these fair caps will turn out to be very useful. Because what we're doing now is we are kind of deciding, do we want to open another box given what we've seen so far? Or are we happy with the price that we found? And the way you can think about this is as follows. Whenever you have a price found so far which is below the fair cap of a box, then the additional value that you're getting from a box will be positive. If you've already found in a price which is above the fair cap, then the expected additional reward that you're getting from opening this box will be negative. And the optimal policy now takes this thought further by understanding that these fair caps actually represent how much you can expect from what's inside a box at any point in time. What we will be considering is the fair cap policy. And what does this look like? We say now, without loss of generality, that sigma 1 is at least, sigma 2 is at least, and so on is at least sigma n. So these are our fair caps. And what we now do is we open the boxes in order 1, 2, and so on, up to maybe n, until the point that sigma I is smaller than the highest value that we've seen up to this point. Then we stop. So we open the boxes by decreasing fair cap, and we always keep track of what's the best price that we've found so far, and then we will at some point see that the largest price that we found so far exceeds the fair cap of the next box that we would want to open, So all boxes at this point have a fair cap of at most this much. Then we stop opening boxes and we take home exactly this price. One way you can understand this policy is to say, okay, these sigma I, these represent how much you can expect to find inside a box after having deducted the costs. Because these costs, they are somewhat paid by the bonus. Those just match up. And so what you can hope to find inside such a box, this is exactly represented by the sigma I. What is interesting about this policy? Well, the one interesting thing about this policy is that we just fix this order in which we open the boxes in advance. We do not change the order depending on our observations. The only thing that depends on our observations is, of course, when we stop opening the boxes. This is why this kind of a policy is called an index policy, as opposed to other policies which might have to react on what they find inside the boxes, and then they might want to open other boxes depending on the observations. This, by the way, is exactly what we will be considering next time. But here, life is easy and life is great because the fair cap policy is optimal. Which means that it maximizes the reward among all policies. So all I want to do now for the rest of today's lecture is exactly prove this theorem. And how do we prove this? Well, we now have to understand what a policy can do at all. Recall that we are now just computing a policy. We're not comparing ourselves to like an offline optimum, which knows inside which box to find what. This is not what we're doing here. We're only comparing ourselves to other policies of the underlying Markov decision process. By the way, this is something I should have mentioned earlier. This problem is, of course, a Markov decision process, but we have an enormous number of states. Namely, we have to keep track of all the boxes that we opened. So in this actually super difficult Markov decision process, this is the optimal policy, is this simple. Let's try to prove this. We'll prove this in multiple steps. Namely, the first thing that we'll do is we will rewrite the expected reward of any policy in terms of the cap values and bonuses of the boxes. How do we do this? So for any policy, we now write that capital I subscript I is 1 if the policy opens box I and it is 0 otherwise. And we let AI be equal to 1 if the policy keeps the price from box I. And also 0 otherwise. So those are random variables that of course depend on what is inside the boxes. And why do we call them I and A? this here we say that the box is inspected, and here we say that the box is accepted. And now we can write the following. The expected reward of any policy pi is given by v of pi. This is the following. Take the sum of all expectations of ai times kappa I minus ii minus ai times bi. So let's understand this in words, what this means. We have the ai, which means what is the price that we're taking home, and we have the ii, which is do we open this box or not. And now we say that the expected reward of any policy is given as follows. It is ai times kappa I minus ii minus ai times bi, and that we're taking the sum of all boxes I. So the expected reward of the policy is given by this, take the sum of all boxes I, or well, we have only one of the ai, of course, being 1, so this is the expected cap value of the price that we take home, and from this we'll have to subtract for every box which we open but do not take home the respective bonus. Good, let's see why this is true. Importantly, this is only true in expectation. This is not the reward. So what you find inside the expectation, this is not just always the reward, because it might happen that sometimes you see much more or sometimes you see much less. This equation only holds in expectation. And let's prove this. So what is v of pi? Well, this is actually, take the expectation of the following, take the sum of the ai times vi minus take the sum of the ii times ci. So here we have the price that we're taking home, and here we're subtracting the cost of what we find, the cost of all the boxes that we open. So we can now rewrite this. Namely, let's move out the sum of all I, and now we have inside ai times vi minus ii times ci. Let's again use linearity of expectation. Recall that the cost of opening a box is not a random variable, so that will be constant. And now we write this in a very important way, namely what we'll do is we'll replace this vi by kappa I plus bi. And why is this correct? Well, here we are using that vi will always be kappa I plus bi. Well, this is nothing but the exact definition of kappa I and bi was that we were splitting up the value between kappa I and bi, which was the overall value was vi. Good, let's now go further. We'll now have the expectation of ai times kappa I plus the expectation of AI times BI. And what do we know about this part here? What do we know about CI? Well, we know that CI is equal to the expectation of BI. So we can also replace this here. And now something really important happens. This is the only reason why this is true. But namely this here, this is the expectation of II times BI. Why this? This is true because II and BI have to be independent. Recall that II was saying, do we open box I? And BI, this depends on what is inside box I. So of course, when we decide that we open box I, we don't know what's inside. So here the policy does not know BI when choosing that it opens this box. And now we are done, because now by linearity of expectation, we get that this is the expectation of AI times kappa I minus, and then we get II minus AI times BI, just by linearity of expectation. And this is exactly what we claimed. So now we found a way to rewrite the expected reward of any policy. How do we do this? Well, there's actually nothing spectacular happening here. This is only plugging in all the definitions that we had. And at one point we're actually using that policies don't know what's inside a box when they decide to open them. And now what we'll show is that our fair cap policy maximizes this quantity here. And this is now something that we can do much more easily, because we can even say this quantity here is maximized pointwise by our policy, even if we didn't have the expectation floating around here. So even then the policy would, the fair cap policy would get the highest out of all policies. And before we get there, let's first make some observations that are unique to the fair cap policy, or at least to any optimal policy for that matter. And the first observation is the following. The fair cap policy always selects the box of highest cap value. That is, sum of the AI times kappa I is equal to the maximum of the kappa I. This so far doesn't seem to have any relation to what a policy should or shouldn't do, but this will turn out to be very useful in the proof later on. So actually the policy was defined to say, how was the policy defined? It was looking at the boxes by decreasing cap value, and as soon as it only had boxes of fair cap values smaller than the highest value that it found so far, it stops. And now here we're saying, okay, now this is the prize that we're taking home. Or the box, what we're actually taking home is actually the box of the highest, with the highest prize. Now this is saying we're not only taking home the box with the highest prize that we find, but we're also taking home the box with the highest cap value. And this is not only including the boxes that we opened, but all boxes. And why is this true? Well, how can we understand this? What is happening here? Let's now draw the fair caps of the boxes that we open. Those are something like this. Those will be the fair caps. And here we are seeing all the boxes from 1 to I. And then we'll also see some prizes. And let's write down the maximum prize that we've seen. Initially, we might only see empty boxes, and then suddenly we see something, and then we see this much, and then of course what happens here? Then the highest price that we've seen is above the fair cap, so we certainly stop opening boxes, and this is why we are not seeing any higher price. This is how much we're taking home. So this means now here, this box, this is the last box that we open. And we do not open boxes beyond this line. So let I last be the last index, or be the index of the last box to be opened. Now what do we see here? Which box are we taking home now? Well, certainly this I last box we are taking home, because we do not at all open these boxes. And here this was the highest price that we found. But what are now the capped values? Because this is something that we were actually trying to make a statement about. Well, what's the cap value of the boxes here? Those are the actual values. Then from here onwards, the cap values are, well, the fair caps. So here the values are not capped, here suddenly the values are capped. And this is exactly the point of our fair cap policy and why this statement is true. Because as soon as one of the values gets capped, we get to stop. So everything that's here is not capped, and everything that is here is being capped. Let's try to write this down more formally in different cases. So we also write I star to be the index of the box that we accept. And now we'll do a case distinction, namely what happens if this value of the box I star, that the price inside the box I star, is no more than its cap. That means that kappa I star will be equal to V I star. And now, for every box that we open, recall that we open all boxes until I last. We have the following. We have that kappa I is at most Vi. Why is this? Because otherwise we wouldn't have opened this box. If one of the Vi, or we would stop earlier. If this was not true, then we wouldn't open box I last, for example, because at the box I last, we would then have that Vi, that the highest Vi that we found would be more than kappa I, than sigma I. Good. So what else do we do? Well, I star is the price that we take home, so all the prices here, they are certainly no more than I star. And how big is Vi star? We said this is kappa I star. So we now have that for every box in this part, the capped value is no more than the capped value of the box that we're taking home. Now, let's also consider the other boxes. The boxes that we do not open, what do we have for them? For them, the capped value will be, well, just the oh, now I realize I said something incorrect here. These first steps, they are coming from what? From where? They are coming from the fact that the cap value is never more than the actual value, and the cap value is never more than the cap. So this is where they are coming from. Now, what is happening here? The cap value of the ith box, where I is bigger than the last, this capped value is certainly no more than the fair cap of the first box that we do not open. And we do not open this box because we stop opening boxes, because we find a price of Vi star, which is bigger than all remaining capped values, fair caps. And now we said that kappa I star will be equal to Vi star. So let's maybe go back to this picture. We now showed that actually we were not in this case here. We were rather in a case where these red dots are maybe like here. Then we actually stop opening boxes because the fair caps are getting too small. There's the other case in which Vi star is bigger than sigma I star, which means that kappa I star will be equal to sigma I star. That means that the price that we're taking home has to be above the fair cap, so the cap value is only the fair cap. In this case, what is it that is happening? This is now the picture that I drew here. Here we are taking home this prize because now we certainly stop opening boxes as soon as we see at some point this here happening, that we see a new price which is above the cap. Then we stop opening boxes, because then of course everything will be below this particular line. So in this case, we take home the last box that we open. Because also the fair cap of the following box, of the box following the one where we found our prize, will be of course no bigger than the fair cap of the box where we found it. So we do not open box I star plus 1. And now let's again consider the two cases. For every box that we did not open, that we did open, we have that kappa I is no more than Vi by definition. This is no more than sigma I last, because we did not stop opening boxes then, and this is equal to kappa I star. And we'll have one final case, namely that for I being bigger than I last, we have that kappa I is no more than sigma I. This is no more than sigma I last by monotonicity, and this is equal to kappa I star. And this overall concludes our claim. And why is that? Well, what we now observe here is that what is kappa I star, and how does it compare to any other kappa I? We see that in this case, any kappa I will be smaller than kappa I star, or also here. Or also here we have that kappa I is smaller than kappa I star, or also here we have that kappa I is smaller than kappa I star. And this holds pointwise, meaning regardless of the random outcomes, we will always have that the prize that we're taking home, that for this prize we have that the capped value of this prize is the maximum of all capped values that are there overall, regardless of whether we opened the boxes or not. And this is just because what you see happening here, the cap values are always the lower of the two of these bars and the dots. And so the point at which we stop, we already have a complete picture of what cap values can be around there, because here all cap values can only be as high as these blue bars, so we do not have to open the boxes anymore to ensure this property. Good. This is the first part. Now we have another part, and then we come to the final conclusion, why our policy is optimal. Namely, the other part is that the fair cap policy always fulfills II minus AI times BI is equal to 0. And this is fortunately much easier to prove. Namely, if we do not open this box, then this will be trivial. Or if the bonus is 0, then this will also be trivial. So all we care about is that we open a box and the bonus is strictly positive. What does this mean? In this case, Vi will be strictly bigger than sigma I, because otherwise the bonus wouldn't be positive, so the value is above its fair cap. And what else do we know? We do not open boxes I plus 1 through n, because what now happened is that the value is above the cap, so all other fair caps that are still around are of course smaller than or no larger than sigma I. And the value found in boxes, the values found in boxes 1 through I minus 1 are smaller than sigma I, because otherwise we wouldn't have opened box I. This means that AI will be 1 because this is the highest price that we find. So this means that II minus AI will be 0. And this already proves this lemma. So this lemma is saying nothing but when there is a box of positive bonus, and if we open this, then this is the box that we're taking home. Let's now combine all of these insights. Namely, there are now 2 insights. This is the one insight. The other insight was that our fair cap policy was taking home the box with the highest capped value. And this now easily implies that we have an optimal policy. Let's consider any policy pi prime and what's the value, the expected value of this policy that we get? It is the sum of these indicators times the capped values and the bonuses. This was our first lemma that we showed. Now this is certainly no more than what we got if we left out this second part. And this can be no more than the expectation of the maximum of these kappa I. Why is this? Because any policy will take home at most one prize, and so only one of these AI prime can be 1, so this can be no more than the maximum of these kappa I. And what else do we know? What do we know about our policy? By the way, I used these indicators with a prime to now indicate this other policy that we were comparing ourselves to. Well, we now know that this here, this will be 0. This is the second lemma that we showed. And this was the first lemma that we showed, namely that we're taking home the box with the maximum cap value. So this will be exactly equal to the expectation of the maximum of all kappa I. And so in total this means that V of pi prime will be no more than V of pi. So this is a remarkably simple proof. How does this work? Well, we have now actually 3 components. The one component was that we can rewrite the expected value of every policy by this term. And now we see, okay, our policy among all maximizes this term. Namely, this term is always no more than the expectation of the maximum of the kappa I. And our policy's expected reward is exactly the expectation of the maximum of the kappa I. Namely, these were the other 2 components. We are always taking home a box whose cap value is highest among all boxes, and we never open a box which has a positive bonus, but we're not taking home this box. Good. So this concludes this proof. We've now seen the optimal policy, and maybe you don't remember that the optimal policy is really this easy. We only have to compute these fair caps, and we only have to then open the boxes by decreasing fair caps. So this is really easy to compute also. It doesn't really matter that we have exponentially many states in our Markov decision process here. Good. So I have to say I still have a little hard time getting a good intuition about what's happening here. Certainly I hope I convinced you that it is easy to realize that all of these inequalities hold, because there were like only 3, 4, 5 inequalities that we were using, and those were mainly coming out of simple case distinctions. This was, I think, the biggest proof that we had here. The intuition I have nonetheless is that the sigma I, they somehow represent what we can hope to find inside a box. And if a sigma I is smaller than what we found already, then we shouldn't open the box, otherwise we should. Good. So this concludes our lecture for today. Next time we will see that with only a slight twist, this problem becomes much more difficult. Namely, what we'll then not have is costs for opening boxes, but we are just constrained in that we can open only so many boxes. And then suddenly the way that we have to make decisions suddenly changes drastically. This is what we'll do next time. Please do let me know if you have any questions, and in the meantime, stay safe. Bye.